the empirical rule. Now, the empirical rule, as we mentioned, applies to bell-shaped curves that are essentially symmetric, which means they look the same. If you were to draw a line down the center, that should be about the mean of the distribution, and all the data to the right, the shape of the curve should look the same as the shape of the curve to the left. It should look like a mirror image across this dotted line in the center. Now, what the empirical rule tells us is that if I were to stretch a line from here to here, well, actually, let's do this differently. Let's do it this way. First off, let me start my timer. If I were to, what the empirical rule states is that if I were to head in this direction a distance of 3 standard deviations, so we're going to head in this direction 3 sigmas, and I were to do the same thing on the other side, head in this direction a distance 3 standard deviations, or 3 sigmas, then (99.7% of the data of the distribution would be under the curve here. So this would account for 99.7% of the data. 99.7% of the data. Now, if instead we were to go 2/3 of that distance, or 2 standard deviations on either side, I'll draw the lines first, come back and put a little arrow tips on them. So now if we were to go 2 standard deviations, you can see that not as much of the distribution is there, but still quite a bit. If you go 2 standard deviations from the mean in these bell-shaped curves, then you will account for 95% of the data. 2 sigma here. Finally, the empirical rule states that if you were to go 1 standard deviation, so half as far, I'll put a little tick here to show you that that's 1 standard deviation to the left, 1 standard deviation to the right, you would account for 68% of the data. So 68% of the data. That's all the data points that fall in this area. 68% of the data. So that in a nutshell is what the empirical rule states. And because this is generally true, we can use it to make predictions and to solve certain problems. For example, suppose we collect data concerning tornadoes. Let's call it tornado data. And the data we collect is the annual amount of tornado damage in dollars that occurs. And suppose we find that we've taken enough data points, and this thing is relatively bell-shaped, bell curve shaped. So looks something like this maybe. And we do some analysis and we find out that our mean is $900 million. So on average, tornadoes cause $900 million worth of damage, say. And our standard deviation is 55 million. Well, we can use the empirical rule to help us come up with some ideas. For example, let's look at a case maybe. Say we want to know what percent of damage on an annual basis will come in at over $1 million or $1,065,000, because maybe that is as much as we could possibly pay. So what percent of the damages, of the annual damages, will come in over $1,065,000,000? Well, the way we might approach solving this, or coming up with an idea for this sort of problem, is we take that, and I'm going to get rid of the 3 zeros and just put this in terms of millions. So 1065, and I'm going to subtract off 900 to find out what the difference is there. And the difference is 165. So 165 million is the difference between the mean and this number we're talking about. So this number is way over here somewhere. Way over here. 1065. And I want to know what percentage of damage occurs on this little tail over here. So let's figure out, let's take this number and divide it by our standard deviation just to see if this happens to come close to any standard deviations. And 165 divided by 55 actually happens to equal 3. Boy, that was lucky. Well, of course, the problem was set up that way so that it would be essentially a distance of 3 standard deviations. So we know that 99.7% of the data falls between 3 standard deviations. So if that's the case, this tail and that tail added together should equal the difference. So 100% or 1.0 minus 0.997 equals 0.003. So keep in mind, that's this piece and this piece. So we have to take that and we have to divide it by 2. So 0.003 divided by 2 equals 0.0015 or 0.15%. So 0.15% of the years will the annual damage be larger than 1,065,000,000.